Welcome. In that video, we are going to implement the awesome DDPM paper, Denoising Diffusion Probabilistic Models. That's a really nice paper that had a major impact in the machine learning community, on in generative AI in general, that helped the development of state-of-the-art diffusion models, and therefore that also had an impact to the general public. We are going to implement that paper. We are going to implement it on the MNIST generation data task. So these are the results we'll get by the end of this video. I will put the link of that GitHub in the description if you want to have a look at it. If you use it and if it's helpful to you, please leave a thumbs up, leave a stars, but also a thumbs up to the video. All that code is coming from my course on diffusion models. So if you're interested, have a look at my course. For now, it's a bestseller on Udemy. So let's dive into the implementation. We're going to use PyTorch to implement everything related to machine learning. We're going to use Keras, but just following the MNIST data. We're not going to do any ML with Keras. And basically, for the backbone, so the function approximator in DDPM, we're going to use a unit that I implemented in my latest YouTube videos. So if you're interested into that, you can have a look at it. But otherwise, basically, you can use any function approximator for the for the function approximator. You can use any function with your own parameters. So you could use anything else than the unit. So basically, you can really see this unit as a black box if you don't want to dive into it. But if you want to understand how it's implemented, or we use attention in it, or we use or we condition it based on the time step t, you can have a look at my latest videos. Let's start by loading the data using Keras. We can also normalize the data so that they are scaled between 0 and 1. And then we can also implement a helper to sample batch of data. So we take as input a batch size, then we sample some pointers in the training data, and we convert the data at those pointers into PyTorch tensors. We give them the proper size. We used some increasing operation, basically to put the channel in the second dimension. And then we push that to the device. And lastly, we interpolate the data to 32 by 32 pixels, because the unit wants input that are multiple of 16. And that's also the case in most diffusion models implementation. So for example, if you have a look at stable diffusion 1 or stable diffusion 2 code, you will see that when it's loading the data, it is making sure that the data is the size of the data, the resolution is a multiple of 16, and if it's not, it's grouping the data to ensure that constraint. That being said, we can directly move into implementing the diffusion model. So we can take as input t the total number of time steps. Usually it's 1000. The model, so basically that will be the function approximator. In our case, we are going to use a unit on the device. That's going to be usually CUDA. We can create the three main, I'm not sure how to call those variables, but beta, alpha, alpha bar are very common in diffusion models. Here for the beta scheduler, we are going to use also something very common. We are going to interpolate linearly between two values, 1e minus 4 and 0.02. And we are going to use the total number of time steps. Then we can move on to implementing the training function. Again, if you want more details about what are beta, alpha, alpha bar, or you want to understand more the training function, you might want to have a look at my course. I did my best to really make something very easy to understand, and people really appreciate my course. Here we are really focusing on the implementation. So if you are really interested into the implementation, I think you're at the right place. But if you want a more technical understanding, or to have a walk through the paper, my course is more adapted. But basically, implementing the algorithm is very easy, because it's just putting this pseudocode into code. So let's just do that. Let's put that into code. So first we sample x from the training data, and then we sample t uniformly between 1 and big T. So let's just do that. First we sample x from the training data, then we sample t between 0 and t. Here we need to be careful about the fact that it's really you need to be careful about edges cases. In that implementation, I've decided to go from t equal to 1 to t plus 1. That's really a choice as long as you're consistent everywhere in your code. Yeah, so once you've done that, you sample epsilon from a normal distribution, and then you take a gradient step on that that function, and that's as easy as that. So let's just implement that gradient step. So we can, because we've pre-computed alpha bar for every time step t, we can fetch it from our given time step t. So here, because I'm starting from 1 to t plus 1, I need to do this minus 1. Again, as long as you're consistent, that's fine. So I'm computing, I'm predicting epsilon with my function approximator. In my case, this is a unit. And then once I have all the variable I need to compute the equation we've just seen, we can compute it and take the MSE loss between the real epsilon value and the predicted epsilon value. And then we can take a gradient step on that loss. So that's as easy as that. We're already done with the training function. Basically, this training function is just doing one gradient step. So we'll need to call it multiple times in the training loop. We'll do that in a moment. And then we can also implement a function to sample from the diffusion model. And again, this is just we just need to put this pseudocode into code. So first we sample the noise from a normal distribution, and then we will recursively or sequentially call the diffusion model. So if t is greater than 1, we sample z from a normal distribution, otherwise we set it to 0. And then at every time step t, we can denoise xt using this equation. So again, very easy to put into code. We first sample x randomly from a normal distribution. Then we can iterate over the for t time step. So yeah, in our case 1000. There are subsequent papers that improve that. For example, if t is equal to 1000, you need to do 1000 steps, which is quite a lot and very slow. And there are papers that allow to do that in 20 or 50 time steps using better schedulers. I will implement that later, so if you're interested, subscribe. And there are also other papers that also try that really go to the extreme and push that to a single step, but this is with more advanced techniques such as distillation. I will also talk about that on that channel, so again, subscribe if you're interested. So as we said, we can sample z from a normal distribution if t is greater than 1, otherwise we set it to 0. And then yeah, here I'm just doing some reshaping. Here until now t is a single value, but I want t to have the same batch size as basically I try to sample multiple data points in a single at the same time in parallel. So I'm basically expanding the shape of t. And then we can compute xt minus 1 from xt. And for that we need beta t, alpha bar t. And therefore we can retrieve it from because we've already pre-computed them, we can retrieve them for our time step t. And then we can compute, basically what we're doing, we are sampling xt minus 1 given from a normal distribution. So what we do, we compute the mean on the sigma, the standard deviation of the distribution, so the summary statistics, and then we can use them to compute x by sampling from this distribution. And then yeah, we can just at the very end, once we've done all our denoising steps, we can return the latest value, so we can return x. That's as simple as that. Now we can put all the pieces together. So we can create our model, we can create an optimizer, we can create a diffusion model by feeding the function approximator. In our case, that's a unit, but again, you can use any parametric model. And then we can train. So basically, it's super easy. We just need to call this training function, this training step multiple times for a given number of epoch, and then we can do a gradient step. Oh no, sorry, because we are already doing the gradient step in that training function. So yeah, there is nothing else to do. That's as simple as that. We just need to call that function multiple times. On that we can plot the results. So we can sample a given number of images. Here we are going to sample 81 in parallel, so that we can make a grid of 9 by 9 images. And then we can create the grid and plot the images, the samples one by one. and then save the results. And if you run that code, you should get results similar to what we've just seen before. Yeah, I really hope this code will be helpful to you. If it is, please leave a thumbs up. It helps you to notice great content, and subscribe for more content related to diffusion model. Thank you.